Welcome back to the Deep Dive. We are your shortcut to deep knowledge, taking stacks of dense source material, academic biographies, archive articles, complex research, and distilling the essential game-changing insights for you.
And today, we are charting the course of a really singular figure in 20th century mathematics, Kiiti Morita. He was a Japanese mathematician who managed to be a giant in two worlds that rarely intersect, abstract algebra and general topology.
That's right. We're diving into excerpts from an archive article and a very comprehensive academic biography, and our mission really is to understand how Morita's mind successfully bounced back and forth, finding these deep unifying structures in both disciplines.
What makes this story so fascinating is the contradiction it's built right into his legacy. Morita had 87 total journal publications.
Okay.
The vast majority, about 75%, were in topology, the study of shape and space.
Yet the sources are so clear about this. It was his algebraic contributions, that remaining 25%, that made his name a household word within the wider mathematical community.
A very household word, right.
So we're dealing with this case of sheer quantity versus explosive universal impact. We need to figure out the source of that explosive power.
Okay, let's start with the man himself to set the stage. Kiiti Morita was born in Hamamatsu, Japan in 1915, and he died in Tokyo in 1995 at the age of 80. He definitely had a rigorous, formal academic grounding.
Right.
He graduated from Tokyo Higher Normal School, which is now Tsukuba University, in 1936, and later earned his PhD in topology from the University of Osaka in 1950.
But the sources reveal this incredible biographical detail that really defines his work. While his primary university focus was in algebra, he was largely self-taught as a topologist. He built his expertise in that field completely outside the standard academic pipeline.
And that self-reliance, that independence, it fed directly into his approach to algebra, too. He wasn't connected with the prominent, established Nagoya research group.
Which meant he was working in what, a kind of academic isolation?
A relative one, yes. And that isolation, it sounds conceptually interesting, but the sources show it had serious practical drawbacks. He was simply out of the loop.
How so?
Well, key foundational documents like the draft copies of Cartan and Eilenberg's revolutionary text Homological Algebra, they reached him only with great delay.
Oh, wow.
Precisely. That book was circulating among young, connected mathematicians in the early 1950s, but Morita didn't get his hands on it until 1956.
The year it was officially published.
The year it was published. Imagine trying to make world-defining breakthroughs while crucial research is delayed by years.
That raises a really interesting question, though. If he was operating outside the main current and, facing these delays, how did he manage to bridge these two vast fields?
I think you're onto it.
Maybe the isolation wasn't a hindrance, but an enabler of non-traditional thinking.
That is the key insight. His work, whether it was in algebra or topology, was driven by a conceptually unifying approach. And that approach was typically category theory.
I see.
He wasn't constrained by the traditional boundaries because he had to find his own path. Category theory let him look past the individual components, past the specific rings or the specific spaces, and focus on the deep underlying relationships and structures between them.
He was seeking a mathematical universal translator.
You could see that.
That ability to synthesize disparate fields is the core of his genius. So let's trace that unifying thread directly to the algebraic revolution he launched.
Absolutely. The spark for his most famous algebraic work came from a field that wasn't even his. It was Pontryagin's duality theory, which deals with locally compact abelian groups.
Okay, duality. So that's the concept where you can define a kind of inverse structure that holds the same information as the original.
Exactly. So he saw duality in this one specific, kind of limited setting and wondered if he could generalize it.
I see where this is going.
Pontryagins' duality relies on a mapping operation called the contravariant Hom functor. Just think of a functor as a standardized mathematical machine that maps objects and structures from one mathematical world, one category, to another.
Right.
So Morita began to experiment. He started feeding more abstract objects, specifically injective modules over general rings, into this machine.
That experimentation led him down a path to new characterizations of quasi-Frobenius rings, which are very specialized algebraic structures.
They are. And that, in turn, led to the big one. His 1958 paper, Duality for modules.
Which contains Morita's theorem on equivalence.
It does, and the sources don't mince words here. This is one of the most frequently used single results in modern abstract algebra.
Okay, let's unpack Morita equivalence for everyone listening, because this is the explosive idea. What does it mean for two rings, let's say other dollars, to be Morita equivalent?
It means that if you look at the entire collection of objects you can build over ring dollar, what mathematicians call the category of modules over a dollar, or a dollar, that whole category is structurally and functionally identical to the category of modules over ring dollars.
BAMOD.
Right, BAMOD. They are mathematically interchangeable, even if the rings or a dollar look nothing alike at first glance.
Wait, okay, so if the categories are identical, why do we need two different rings? Why would a mathematician bother with the more complicated one?
That's the brilliant paradox. The equivalence allows mathematicians to cast technical ballast overboard. Think of it as a computational free pass.
A free pass.
Yeah. Often the property you want to study is much easier to define or prove in the simpler, smaller ring, or dollars. But sometimes the properties only manifest or have physical relevance in the more complex structure, bar dollars.
Oh, I see.
Because of Morita's theorem, if you prove a structural property holds for the simple category a bar dollar, you know it holds for the complex bar dollars without doing any extra work.
That sounds like an astronomical increase in efficiency. You can study the structure that is easy to manipulate and just instantly apply those findings to a structure that is maybe computationally impossible to handle otherwise.
That's it exactly. The source gives a specific example that a ring dollar is Morita equivalent to the dollar by no matrix ring.
So the matrix ring is way more complex.
Far more complex, but its underlying module category behaves identically to the simple ring a dollar. This unified framework, as the sources describe it, rapidly built a network of such bridges linking and unifying extensive parts of algebra.
And the way this idea spread was fascinatingly old school. It spread across the US and globally in the early 1960s through mimeographed notes, just copies of notes based on lectures given by H. Bass.
It truly went viral within the mathematical community, 1960 style. And the ripple effect continues today, and this is where Morita's generalization powers become truly apparent.
You mean it goes beyond algebra?
Way beyond core algebra. We see M. Riefel using it to develop Morita equivalents for C algebras and W algebras.
Which are crucial in quantum physics and functional analysis.
Exactly. And it even extends to Banach algebras and Poisson manifolds.
So Morita took a specific insight about groups, generalized it to rings, and now the idea of equivalence is foundational for structures used to describe particle behavior in complex systems.
It is the ultimate example of abstraction driving physical and mathematical progress. And what's more, Morita's vision paved the way for Morita theory for derived categories, completely characterized by J. Rickard in the late 1980s.
This is what, exactly?
It's essentially applying the equivalence concept not just to the modules themselves, but to the deep homological connections between the modules. It shows his initial insight continues to be the starting point for decades of advanced research.
That gives us a powerful sense of his algebraic legacy. Now let's pivot. We've been talking about this massively influential 25% of his publications.
Right.
How do we make sense of the other 75%, the foundational work in topology? What conceptual thread did Morita carry with him from the algebraic world into the geometric world?
He carried that focus on unifying structure, often mediated by category theory or, concepts that were category adjacent. Just as he asked, when are two algebraic structures equivalent? In topology, he asked, how are different geometric properties connected?
And under what conditions do these properties remain stable?
Exactly. His work there established him as one of the great founders of modern general topology.
So we can group these achievements into three major areas, right? Starting with his work on paracompactness and normality.
Yes, and this involved making these deep connections between seemingly distinct properties of a space. For example, he proved that every regular Lindelöf space is paracompact, which was a significant generalization at the time.
But the unexpected link he established between paracompactness and normality is the one that really stands out in the sources.
Absolutely. Paracompactness means that every open covering of a space can be refined into a locally finite one, which is crucial for building algebraic structures on topological spaces.
And normality is a separation property, the ability to separate disjoint closed sets.
Right. Two very different sounding ideas. But Morita showed they were linked through products. He proved a space 6 Pasterval is a paracompact if and only if the product of $6 with any compactification of $6 is normal.
That's incredibly elegant. It connects three major properties in one unified statement.
It's beautiful. And next, we have to look at Morita's conjectures. This part of his story truly highlights his power as a problem poser who could shape a field for generations.
How so?
Well, his 3 conjectures on normality of product spaces, basically, how 2 normal spaces behave when you multiply them together, became these incredibly influential, difficult challenges. They weren't trivial side questions, they struck at the very heart of structural stability and topology.
I noticed the second conjecture was so profound it required more than just advanced geometry to solve, is that right?
That's where the human drama of pure mathematics really comes in. The second conjecture was only answered in the affirmative by Chiba, Przynski, and Rudin, and it required leveraging an additional deep set theoretic assumption known as Villobin.
So for anyone listening, that's a huge conceptual leap. You're saying that to answer a question about the shape of a space, mathematicians had to reach into the most fundamental abstract assumptions about how we build the entire mathematical universe.
That's exactly it. Via Lawler's is the assumption that the universe of sets is the smallest possible model, a very technical and very powerful assumption. The fact that Morita's questions forced researchers to this extreme level of abstraction just underscores how deep his insights were.
And the other conjectures?
Well, his third conjecture was only recently confirmed by Z below. He also introduced the notion of an M-space.
And M-spaces are a great example of that structural unification we keep talking about.
They really are. Morita defined M-spaces abstractly, but then J. Nagata provided this beautiful characterization. He showed M-spaces are simply spaces that are homeomorphic to a closed subspace of the product of a metric space and a compact Hausdorff space.
Which makes the abstract concept concrete. It shows M-spaces aren't some esoteric concept floating in the ether.
Not at all.
They're closely related to the easily understood, well-behaved world of metric spaces.
Precisely. And finally, we move to dimension and shape theory. In dimension theory, Morita, working independently with M. Katoff, settled a major dispute. He established that the covering dimension, Tex, equals the large inductive dimension, Tex in dimension, for arbitrary metrizable spaces.
So essentially showing that 2 different methods of measuring the complexity of the space actually give you the same result as long as the space is well behaved.
Yes, unifying 2 parallel measures of complexity. And he also extended the highly sophisticated field of shape theory to general spaces, which he did independently of S. Mardeja. He did this by leveraging P.S. Alexandrov's idea of the nerve of a locally finite covering.
That phrase, the nerve of a locally finite covering, sounds highly technical. What is he doing conceptually there?
It's a very elegant act of translation. He takes a messy, general space and covers it with small, overlapping sets. The nerve is a geometric object. It's a kind of blueprint that just records which of those sets overlap. By assembling these blueprints for finer and finer coverings into something called an inverse system, he created a standardized way to describe the shape of the space, even when the space itself is too complex for traditional algebraic tools. It's the ultimate combination of set theory, category theory, and geometry.
So if we synthesize Morita's entire body of work, from the matrix rings to the M spaces, what is the central legacy?
It's his unique ability to see structure where others saw only individual components. He applied category theory not just to simplify algebra, but to provide a unified structural framework for geometry and topology. His work supplies, as the source says, immensely useful results, and it contributed strongly to the present mode of thinking about mathematical structures.
He was the great conceptual bridge builder.
He really was.
And his influence was certainly global, which is especially notable given his isolated start. The sources confirm his ideas profoundly shaped mathematical schools in Japan, the US, and the former Soviet Union.
And beyond the mathematical structures, we should remember the human structure. One colleague recollected Morita as a very warm, hospitable person with a lot of humor and benevolence. It's a wonderful footnote to note the man who unified mathematical concepts was also a unifying figure among his peers.
It definitely completes the portrait of a mathematical giant. As we conclude this deep dive, let's reflect on the core lesson for you, the listener, regardless of your field. Morita's breakthroughs were universal, achieved despite working in relative isolation early on, and based on self-taught knowledge in a secondary field.
The power of his career lies in his relentless drive toward generalization. He saw duality in a niche area and spent his career generalizing the core concept of equivalence until it transformed fields ranging from abstract algebra to quantum operator theory. So the final thought we want to leave you with is this. If a unifying concept initially derived from an obscure duality theory can build bridges across all of modern mathematics, what fundamental concept is currently locked away in a niche field and, well, perhaps in coding, biology, or economics, that is waiting to be generalized and transform our broader understanding of complex systems.
We'll see you next time for the next deep dive.